Hi, and welcome back for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. During the last episode, we finally met with the power of Quadratic Sieve. Now we are going to do some minor optimization of Sieve of Eratosthenes and some cleanup. So Sieve of Eratosthenes is basically a very ancient method of finding prime numbers. It starts with a 2, then it marks all the values that's divisible by 2, working on some metrics. Then it moves to 3, marks all the values divisible by 3, and then everything that it's left, it's a prime. So I implemented that. Um, this is the algorithm. I made a small optimization where instead of using a full array, I'm using just half of the array, and I'm taking 2 as an obvious prime. So I'm having some translation between the actual limit, the actual value to that smaller array. Okay, and it turns out that this method is super fast. Let me just show you. So going for a million, limit of a million, yeah, 39 milliseconds for 78k primes. That's a lot. Okay, so let's integrate it. Allow new trick. Yes. For duplicating file, this is much nicer. Now close, close, and we are on episode 7. Great. So now let's update the prime base using Sieve of Eratosthenes. I'm probably not pronouncing it right. Okay. Also slightly change our logic. Instead of telling that we want to create b prime values, we are saying that b is now our limit, which, by the way, aligned with the definition of that b bound in wiki. Okay. Now for each prime, we want to check on that. And since we are working with integers now, it will be a good idea to also switch working with integers everywhere else. Yeah, what we've been using, actually that needs still to get the big integer value. So integer prime. And prime base, let's turn that into integer. Now we also need to update the Gaussian illumination metrics, and that used by other episodes. So let's duplicate that. And work with version 2. So now it's just an integer. And so in here, just an integer. It's not been used. We just need the size here, so let's switch it to prime size. Prime base size. Yeah. Oh, and there is a bug in this implementation. The bsmooth index that we are testing can get twice into the map because there is another for loop going on here. The testing if we want to filter each of those primes, and one prime can have two indexes, two primes that are not that nobody else is having, and so it can enter twice into the map. And if that happens, then we will have duplicates and we may run out of bounds when doing this. So to fix it, we just add a break here. So that part is fixed. Next, set it to integer as well. We are building wheels, and we don't need to convert it to long, just a prime. Oh, and wheel needs to change. Yeah, it also using the long version of it. So let's duplicate this class as well. And now let's replace wheel as well. Yeah, just the words. Place. Yes. Now we can update it to be long. All right. Another one. So in here we do need to use the big integer for the vector extraction. Yeah. Let's see if it still works. Oh, one thing that it's changed, it's our logic. So B is no longer tell us that it's going to be 5,000 primes, but the biggest prime is 5,000. So we need to increase it to about 20k. I'm not sure. Let's see. Yeah, just 1k primes. So let's increase it to 80k. 4k primes. Let's see if it will work. Okay, let me check. Okay, so during the find bsmooth values, the condition is not that bsmooth size is bigger than b because it's not longer our prime base size. This is what we want. Okay, let's try again. I played with the numbers here. Okay, no solution found. So maybe let's increase the size of the values that we are collecting. Prime base size, let's say, times 1.5. It's a magic number that we need to work with. Could happen that we didn't find a solution. So it worked now. Okay. Another optimization that I would like to introduce, it's here. That one. What will happen if we play with that number? And it's also yet another magic number that we need to optimize. We said previously that it could be that our reminder, if we choose it to be at most the size of our biggest prime in the prime base, then it's guarantees that it's going to be a Bismuth value. But what if it's not guaranteed that it's going to be a Bismuth value? What will happen? Then our extraction of the vectors will not be perfect, as it was here. Only 2 failed. Many will fail, but it will be easier for us to find those values. So let's try this again. Yeah, so now it worked faster, and it found less prime values. It extracted much less values, but it gave us bigger speed. And it's even worthwhile checking increasing that. All right, we solve it pretty quickly. 12 seconds while I'm recording. So this is great. We did some small optimizations. We're pretty much hitting the speed of this algorithm. So the next optimizations will not move this value much further, but it's going to improve. So stay tuned for what is coming next, because they're going to talk about some really nice low level optimization things. If you have any questions, please post them in the Facebook group or comment below. The source code will be available on GitHub. See ya!